Hi, everyone. Today's lesson is about potential energy diagrams. And so, if you're describing how a reaction will proceed, what you can do is you can use a potential energy diagram. I have a potential energy diagram here for you right now. And so, you have reactants, and they have a certain amount of energy, and then they follow this pathway until they get to the products. And this is called a potential energy diagram or a potential energy curve, right? We see this curve here, and it's showing the amount of energy that will be there in a reaction. So energy released or absorbed by a chemical reaction can be described by this here potential energy diagram. And so the way that I like to think of a potential energy diagram is actually with the roller coaster King to Ka. Now, for those of you who are familiar with King to Ka is this massive, massive roller coaster. You start down here, and the roller coaster slingshots you all the way up this giant curve until it gets to the very, very top. Then up at the top, it will drop you this way. Or so I'm told, because the one time that I went on it, I passed out. And the reason that I passed out is because as we were loading onto the roller coaster over here, I looked behind me and I saw some rather large individuals that got onto the roller coaster. And I thought, oh my gosh, there's no way we're going to get launched all the way up over this curve. These people behind me are just way too big. So they got on, and I'm like, okay, how is this really going to go? And so they launched us. And we went up, 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 all the way up to about here. And we didn't quite make it over the top. And so what happens if you don't quite make it over the top is that you fall back down, or so I'm told, because at that point I had completely passed out. My wife was enjoying all of it, but we went all the way back down to the start. In which case I woke up, I asked my wife how the ride was, and she said, we haven't even started because, there were some kind of large people on the ride with us. So they launched us again, and off we went, and up and up and up and up and up and up we went, but we didn't have enough energy to get over the top of that curve, and back down we went. And finally, the third time we went up, we went over, and we went all the way to the end of the ride. Now, that King to Ka experience that I had is very similar to the way potential energy diagrams work, right? We always read them from left to right, and you start here where the reactants are. If you don't give the reactants enough energy to get up and over the top of this curve, the reaction will not proceed. When the reaction does proceed, we say that it goes to completion. Completion would be when it produces the products. But if it doesn't go to completion, well, then it's not actually going to get up over this curve. You're not going to have enough energy. And the way that we describe this is actually through the term activation energy. So if you see EA here, EA represents activation energy, and it's the amount of energy needed to go from the reactants all the way to the top of the potential energy diagram. The potential energy diagram's very top has a name as well. That part is called the activated complex. So this activation energy, or EA, is the amount of energy to go from the reactants all the way to the top, which is called the activated complex. And now from the activated complex, and when it goes back down to the products, obviously this area would be called the product. So right here, what I'm introducing you to is the idea of reactants. That means that this arrow right here that goes from the bottom to the reactants is called the potential energy of the reactants. Then we've got this arrow, which goes from the bottom to the products right here. This is called the potential energy of the products. And then you've got this idea of this amount of energy needed to go from the reactants to the top, which is called activation energy. All right, so as we continue with that, let's take a look at our next question. I'm going to put this in full screen so that we can really see it, and we'll look at this. There are two different types of potential energy diagrams. There's exothermic, like I have here on the left, and there's endothermic like I have here on the right. You'll notice if you look at the potential energy diagrams themselves, the reactants lose energy when they're considered exothermic, and the reactants gain energy when they're considered endothermic. Another way of thinking of that is that the reactants have more energy than the products, right? Heat is being released, or energy is being released, whereas here, energy is actually being gained. It's going from low energy with the reactants to a higher amount of energy with the products. So when you have exothermic reactions, the potential energy decreases because it releases energy, right? Well, delta H, which we know as enthalpy, which now we're also calling heat of reaction, will be negative. And we're going to talk about delta H in a second. But delta H is actually calculated by subtracting the energy of the products minus the energy of the reactants. Now, obviously, in an exothermic reaction, the products will always have less energy. So potential energy of the products minus potential energy of the reactants will always be negative. And if you look here, delta H is positive. We still calculate delta H, which is called heat of reaction, by taking the potential energy of the products and subtracting the potential energy of the reactants. And we know that in an endothermic reaction, energy is always being gained, so it's actually going to go up. If you look at the location of energy in both of these equations, you'll see exactly what I'm talking about, right? Exothermic reaction produces energy. It means it gives it off. So obviously, the products have less of it because they're producing the energy. Whereas over here, the reactants are the ones that are gaining the energy, and that's considered an endothermic reaction. So when you look at these curves, you can easily tell which one is exothermic and which one is endothermic just by looking at the curve itself and saying, okay, well, the reactants have lost energy when they became products, so that's exothermic, energy exited, right? Exothermic, think exit. And here we have the energy being gained or absorbed, so I would think endothermic, entering, right? The energy is entering this reaction, and so it's going to be going up when it becomes a product. Let's see if we can answer this question together. According to table I, which potential energy diagram best represents the reaction that forms water as a liquid from its elements? So you would go to table I and you would look for H2O liquid, and then you would see it being formed as a product, so it should be on the right, from its elements. We know that H2O is formed from hydrogen and oxygen. So you're going to go to table I now, take out that reference table, and you're going to say, okay, is delta H positive or negative? If you see on table I that it's actually losing energy and delta H is negative, that's going to be exothermic. If you see on table I that instead it's going to gain energy, that would be a positive delta H value on table I, and that would show you that it was endothermic. Obviously, we know that choices 3 and 4 are nonsense because they don't look anything like the potential energy curves I've shown you. So we're going to rule those out immediately. But out of 1 and 2, I want you to tell me when you go to table I, what you see. Do you see a negative delta H, meaning the products are lower than the reactants? Or do you see a positive delta H, meaning that the products are higher than the reactants? Please look at table I now and answer this question. Okay, you clearly saw that according to table I, it was a negative delta H. That means energy was being lost, and so the reaction would look like this. Let's take a look at another practice question. Which statement correctly describes an endothermic reaction? Well, we know that endothermic, right, has what type of potential energy? Is it being absorbed? Is it being lost? And what does that tell us about the heat of reaction? Heat of reaction, again, is delta H. Is delta H positive or negative in an endothermic reaction? Why don't you take a look at this question and answer it now? We know that products have higher potential energies than their reactants in an endothermic reaction. So you should have noticed that it was going to be higher and ruled out choices 3 and 4. Now the question is, well, what about heat of reaction? Well, you do products minus reactants to get delta H, and we know that products minus reactants is actually going to be positive in this case. So we know that delta H is positive and the products have a higher potential energy. So we know that the answer here is choice number 2. Okay, now that we've talked about that, it's important that we consider all of the different facets of an exothermic reaction and an endothermic reaction. So I'm going to go over here to the sketch pad and I'm going to draw a couple of things for you. Actually, this one seems to have a little extra, so let's address that now. What you're seeing over here is called a catalyst, right? So what we know about catalysts from our 6 factors that affect reaction rate, we know that catalysts lower activation energy. you already should be aware that activation energy is the amount of energy to go from the reactants to the top. I drew it a little high. It should have matched up right with the top, which it didn't, but you get my point. So this is activation energy, right? Activation energy. Excuse my handwriting on this computer, but we also call it E with a subscript of A, or some people even call it A with a AE, meaning activation energy, right? You could call it either of those things. And so the activation energy is the amount of energy, think of king to ka, right? Needed to go from the reactants all the way to the top. While we're here, we might as well label these as the reactants, and that makes these the products, of course. And so normally this is how it would work. But here we've got this dotted line. This dotted line is what we call an alternate reaction pathway. I'll put it in quotes for you. Alternate. Let's finish that. Alternate reaction pathway. And so when you look at an alternate reaction pathway, what I'm saying is normally you need this much energy. That's a lot of energy to get over the top for this reaction to happen. But if you go from here only to the top where the catalyst is located, well, then I could label that, and in fact I will, as activation energy with a catalyst. And that obviously makes sense to me because it's producing or providing that alternate reaction pathway. Instead of having to go all the way up there, it needs much less energy because there's a catalyst there. So you could even call that with a catalyst, or you could say in the presence of a catalyst. They both really mean the same thing here, so it doesn't really matter. We know that if we were to go from the bottom to the reactants, this would be the potential energy of the reactants, right? And then if we went from the bottom to here, that would be the potential energy of the products. Now, I understand that this is a lot to memorize, and this entire diagram is not so neat, right? It's not the nicest way of looking at things. And in fact, I have so much more to label. I don't want to overwhelm you with all of this information, so I'm actually going to give you another diagram. Now remember, the products are higher than the reactants here, so this is what type of reaction? It's an endothermic reaction because they're gaining energy. And so now I'm going to bring you over to this reaction, and this one is what? What type of reaction is this? This is an exothermic reaction because it's losing energy. Now I already know that these are the reactants, these are the products. I know that going from the bottom to the top here is the potential energy of the reactants. I know that going from the bottom to the top here is the potential energy of the products. This, again, as I told you earlier, is called the activated complex. Should be a D written here, but didn't quite fit. There you go. And so if I were to draw a line from the bottom all the way, this line should be straight. I'm so sorry. If I were to draw this to the top, this would be called the potential energy of the activated complex. And lastly, the amount of energy in between the products and the reactants, right? So let's see if we can maybe draw this again. Would I be able to do that? I don't know. I don't want to chance it. So let's just draw a dotted line from over here. So if I were to go from the reactants down here, you know that this matches up with where the products are, right? These are the products. So if I were to go from here, these are the reactants. If I were to go from here to here, the difference, the products minus the reactants, that's called delta H. And delta H, as I will tell you over here where I have a little more room, delta H is called heat of reaction. It also has another name that you've learned in class, and that other name is enthalpy. You already know that. You know all about enthalpy already, right? We talked about enthalpy being a